Welcome to Rust for Windows, a new series for Windows developers wanting to learn how to make the most of Rust as a Windows developer. My name is Kenny Kerr, and in this preparatory installment, I'll show you what you need to turn your vanilla Windows dev box into a Rust developer machine. I'm going to assume you have a recent version of Windows and have already installed Visual Studio. You'll mainly want to make sure you've installed the Visual C++ Developer Tools workload. You also have other options in terms of using the standalone Visual C++ build tools or even a different C++ compiler. But Visual Studio is just the simplest way to get started. Rust can target any toolchain, but on Windows, Visual Studio is just the default and preferred toolchain. Keep in mind that Rust does not depend on C++ itself. It does, however, at least for now, require a linker and happens to use the same object and debug formats as your local C++ toolchain. Not that you ever have to really think about Visual Studio again, nor will you want to after you see how straightforward and easy the Rust toolchain is as an abstraction. So now let's open the browser and find the Rust bootstrapper called RustUp. You can search for Rust's website one way or another. One option is to hit the Get Started link. And there's the link to the RustUp installer. Alternatively, you can go directly to rustup.rs, and there again you'll find the same link. Let that download, and you can see I've already downloaded it in the past. But as you can see, this is just a standard command line installer. You proceed with installation, and it takes care of the rest. And in moments, you'll have the Rust toolchain installed on your machine. Once this completes, you're almost ready to begin your journey as a Rust developer. The only thing left, at least to get started, is VS Code. A good IDE is priceless, and VS Code naturally supports Rust out of the box. From this point on, you can simply run RustUp on the console as needed to update your Rust toolchain to grab the latest Rust compiler or install an optional toolchain component. Okay, let's now get started for real. We'll be going through a number of topics about this memory-safe systems programming language, not the least of which is memory safety and security. But in this first installment, let's hit the ground running by calling a couple of APIs. If you've lived blissfully unaware of Windows these last few decades, it is an operating system full of APIs or system calls. Various programmatic features ready for developers to exploit and combine in weird and wonderful ways. Without a desire or necessity, calling Windows APIs is a big part of Windows programming. Let's create a Scratch project or package that we can use to write some code. Cargo is Rust's build system or package manager, basically the central and largely only tool you'll need to drive your development workflow. Here we've just created a new binary package or project, and we'll go ahead and open that in VS Code. This is where you'll live as a Rust developer on Windows, or really any platform. In the Explorer panel to the left, you'll see that Cargo created a simple folder structure. You honestly didn't need Cargo to create this for you, as it's so straightforward, but it helps nonetheless. This is the manifest or description of your project, what Cargo calls a package or crate. It's just where the package-specific configuration lives in a very simple format, so no IDE is required to try to make sense of it. You don't need an XML parser. You can just edit this directly as needed. Now we'll explore this more deeply later on. You'll notice that Cargo favors Git and creates a default git ignore file on the assumption that you'll soon be pushing your code to a Git repo. The target folder is excluded by default. This is just where Cargo will by default write build artifacts in output. This is of course optional, and you can delete the git ignore file if that's not for you. And there is the meat of the package, with a one-liner to welcome you to the world. You can go ahead and use Cargo again to build and run it as follows. Congrats! Perhaps you've just built your first Rust project on Windows. Now about those Windows APIs. Just like this sample package, there is a whole ecosystem of other packages. Either binary packages like this one, or library packages often called crates that can be shared and depended on. Such dependencies are described in the package's cargo.toml file. This tells Cargo to hit up the crates registry looking for a crate called Windows. A quick diversion. Here you can see the default public crates registry online at crates.io. And I can go to the Windows crate where you'll find information about the latest versions, documentation, and so forth. Just FYI, we'll explore the crates registry in future. Now back to VS Code. We'll tell it what version to use, and we can enjoy semantic versioning and avoid all the trouble with library dependencies in languages like C++. Finally, and this is a bit of a big feature, but crates can themselves be conditionally compiled to avoid pulling in each and every feature, mostly to reduce build time for a large crate like Windows. So, we'll just add a single feature. In this case, we'll just tell Cargo we'd like to use the APIs from the Win32 system threading submodule. Rust code within a package is logically structured into modules, somewhat like namespaces in C++ or C#. Excellent. Let's rebuild and see what happens. And just like that, Cargo chases down the new dependency and any dependencies that it has, making sure everything you need to build and link for the current target machine is primed and ready to spit out code. Don't worry too much about what's all going on there. Just realize that in a few seconds, you went from a vanilla Rust environment to a fully loaded Windows development environment at your fingertips. And of course, Cargo caches all of this for you, so the next time you build, it takes no time at all. Okay, let's write some code. We can employ a use declaration to make these APIs a little more accessible. This is not unlike a using namespace declaration in C++ or C#. Now, in order to prove that the code works and yet keep it real simple, let's just use the thread pool to increment a counter some number of times. We can use this reader-writer lock from the Rust standard library for safe and multi-threaded access to the counter variable as follows. For this example, I'll just use a simple main function with a big unsafe block, since virtually everything here is going to be unsafe. Why is that? Well, the Windows crate lets you call foreign functions, foreign to Rust anyway, and these are generally assumed to be unsafe. We'll talk more about safety and unsafe code in due time, a very important topic as we think about security and memory safety. The Windows crate also offers rich error handling, critical to realistic systems programming, so we'll just update the main function to handle error propagation as follows. Rust's approach to error propagation is pretty neat, but we'll explore that some other time. Okay, let's call some APIs. The threadpool API is modeled as a set of objects exposed via a traditional C-style API. The first thing we need to do is create a work object. The first parameter is a pointer to a callback function. The remaining parameters are optional, and you can read more about them in my threadpool series on MSDN. The callback itself must be a valid C-style callback according to the signature expected by the threadpool API. Here is a simple callback that we'll then use to increment that counter. The parameters can safely be ignored, but do come in handy from time to time. Perhaps we'll do a thread pool deep dive in future. For the sake of this example, we'll just increment the count from within the callback to prove it's being called. This might seem a little unusual with writes and unwraps, but you'll quickly start recognizing the patterns from the Rust standard library. The write is just requesting a write lock on the reader-writer lock. The unwrap is just asserting that the lock isn't poisoned. You can technically handle lock poisoning, but will not do so here. The unwrap will effectively panic. At this point, we have a valid work object, but nothing is happening yet. In order to kick off some actual work, we need to submit the work object to the thread pool. You can do so as many times as you like. So we'll just go ahead and do it 10 times to keep things predictable. You can now expect the callbacks to run concurrently, hence the reader-writer lock. Of course, with all of that concurrency, we need some way to tell when the work is done. That's the job of the wait for thread pool work callbacks function. Quite a mouthful. The second parameter indicates whether we would like to cancel any pending callbacks that have not started executing. Passing false here thus indicates that we would like the wait function to block until all of the submitted work has completed. At that point, we can safely close the work object to free its memory. And just to prove that it works reliably, we can print out the counter's value. Here again, we're using the lock's corresponding read acquisition method that can also fail due to poisoning. And let's just print out the sum. And let's see what Cargo has to say about that. Oh, looks like I have a typo. This should be result. Sweet. The system thread pool successfully spun up just enough worker threads to maximize concurrency and system efficiency in the pursuit of getting that work done as quickly as possible, making sure not to overschedule the CPU. Congratulations! You've called a very powerful Windows API in just a handful of lines, and in Rust of all things. We've glossed over a bunch of things, from where these definitions or bindings come from, how linking occurs, wait, there's a linker, yep, and much more. We'll explore it all in due time, so stay tuned for more in this new series on Rust for Windows. Until next time, my name is Kenny Kerr.